Okay, so this is a bit of an overview of Chapter 6 now that we've finished the chapter. So what was Chapter 6 all about? So Chapter 6, hopefully everybody can read that okay, is the Laplace transform. And so the big thing in 6.1 is really the definition, and that is that the Laplace transform of f we could write as the integral from 0 to infinity e to the minus st f of t dt. And so a couple of notes here, right, that this is a function of s when you've integrated out the t, and also this is an improper integral, right, so that we do have to be able to take the limit. And also for what functions f can we guarantee that this integral works? We talked about f is piecewise continuous and of exponential order. What does that mean, of exponential order? Exponential order means that the function does not grow faster than an exponential function. Okay, in words, we can write down the definition f of t less than or equal to some function, some exponential function. So we would have to find the m and the k, and this is for t greater than or equal to some fixed time t. Good. All right. The second main thing that we have here is the linear this is a linear operator. The Laplace transform is a linear operator. Okay, that makes the table easy to use. And so in 6.2 then, the main point here was that you could take the Laplace transform of the derivative of a function, right? And you could write it in terms of the Laplace transform of the original function. So differentiation in time means that you're multiplying by s in s space with a little bit of extra stuff here. We have some extra constants going on there, right? And then the Laplace transform of the second derivative. Similar s squared. So another derivative means you're multiplying again by s, but now we have our other terms here. So it's good to just remember these so you can write them down real quick when we're using this for a definition. You don't want to have to prove it every time. Also, we built a table of transforms. And so that'll be available during the exam, of course. The main thing about this table is we should be able to use the table to compute the Laplace transform and the Laplace transform inverse. Right? Okay. Then in 6.3, I guess 6.2 is where we started to use the Laplace transform for its primary function, and that is Laplace transform is used to solve differential equations, linear differential equations. So how does that work? If I have some linear second order differential equation, for example, that's where we're focusing our attention on. I'm not going to have room to write that. Okay. We have a differential equation in t. We take the Laplace transform and change it to a function of an algebraic equation in S, right? So that's really nice. What we're doing then is when we solve a differential equation, solve in t, we can solve in S. What we typically do is instead of going directly to the solution in time, what we do is we take the Laplace transform of our differential equation, gets us into S space, and then we solve this algebraically. This is algebra now to get us down to here. And then we invert the transform to bring us back to the solution in time. And so that's a really nice, it works out very nicely for lots of different functions. Okay, so the big question then is, how do you do the inverse Laplace transform? And there are some tricks to inversion. We could add and subtract the same number. We can multiply and divide by the same number if we need to. Well, we can perform, what is that? Complete the square. Complete the square in the denominator usually. Um, well, we'll try a few examples. I think this pretty much takes care of most of the tricks that we have to use. And of course, there's ways of dealing with things in the table as well that we'll talk about when we, well, you've seen those in the homework. All right, so what was 6.3 and 6.4 about? I'll try to write straight here. This was about the Heaviside function. And so the Heaviside function is a step function that's 0 up until some point. Okay, and how's the Heaviside function used? It's really used more of as like an on-off switch for power. So if you want, if you have some underlying function here, and you only want to turn it on at time A and off at time B, right, then the function becomes this function, right, with it being 0 everywhere else, if we multiply this on-off switch by our f of t. And so this would be, if this is the graph of f of t here, then this would be our on switch at time A minus our off switch at time B times f of t. And so this is very useful when you're trying to translate some piecewise defined function, right? So if you have one of these that's only true for time A and B, right, then you can pull that out, and this would be your result for f sub 2. And then you could add these pieces on together, right? So you could have your f1 with your on-off switch there, because this is 0 outside of the time, outside of the interval from A to B. Good. All right. Yeah, so 6.3 and 6.4 didn't add too much beyond using the Heaviside function for differential equations. And so we just got some practice there inverting the transform as well. Let's see, so Heaviside function 6.5, what was that one all about? I'm going to pause for a second. Kind of looking over some comments, maybe before we go on to 6.5. If we have something like e to the minus 3s times some expression, s squared plus 1 over some like s cubed plus 2s squared plus s, something like this, and we want to try to find the inverse. The best way to do this is to break this up as e to the minus cs f of s, because then you can go ahead and use the table entry. I was just trying to find which table entry it is in terms of a number. I don't trust my numbers there in front of me right now. But anyway, because when you invert this, right, you just get u sub c of t times f of t minus c. And so the real issue then is only, can you take f of s and give me f of t? Because once I have f of t, it's easy to write f of t minus c. So I would just start with f of s, right? And then I would go ahead and find f of t. And that basically solves the problem, right? Because then you can say, well, my solution is e to the minus, e sub 3 of t times f of t minus 3, where f of t was given up above. Good. So that's a little bit of a time saver. I think I will pause here and get the new different video out for the next couple sections.